All right, and recording started. All right, so welcome to Tuesday. Today's going to be a pretty good day because look at all the fun stuff we got lined up. Let me mention this first. Mr. and Miss VHS. So this is something you can vote on if you are a senior. Let me switch my screen. They present screen 2, share. Okay. So I posted a link for this on your guys' Google Classroom to show you guys exactly where to find it. So I did put this on the review section, which is coming up pretty soon anyway. So see, top link here says vote link for Mr. and Miss VHS. So just if you're a senior, so senior, here's your options for vote on. So there you go. That's what that link is. So stop sharing the screen. Right, back to agenda. Right, so rest of today, and this agenda plan out fits exactly in the block, so works out perfect. I've got a few Paul Hewitt demos lined up for you guys related to electromagnetism. Then I've got a bunch of fun stuff around on my desk. Got batteries and bolts and wires and got some 9 volts. Got some magnets around here. So gonna show you guys how to construct. Got some little LED lights. Okay. Show you guys how to construct a bunch of fun stuff. Compass, electromagnet, motor, with just some basic stuff you can find lying around. Okay. I do want to show you guys how to use a multimeter. Okay. So this guy right here, and I wanted to introduce you guys to this idea. I wish we had a breadboard around here. I was digging around the closet. I was thinking there was one, but guess not. Oops. But I've got a video anyway that shows how breadboards work. If you guys get into electronics or robotics and you want to be familiar with this, know how to work your way around one of those. Then near the end of class, or actually this will take us to the end of class, we're going to do a couple of labs. Now, I've really shortened these, so we'll do short versions of these. I'm not going to have you guys do the write-ups or anything. But at home, you'll want to print off a couple of pages. One page that looks like this. It says Kirchhoff table for circuits lab. We're only going to use just one small piece of this, just for just so you guys get the idea of how this works. Okay. Also, what you want printed, if you're in class and this is printed on the other side of the page, just gave you, is Resistivity of DOLAB. These are both posted to Google Classroom under the electricity section. Right. I've got some Play-Doh right here. Turns out that Play-Doh is conductive, kind of like copper wire is conductive, okay? Which means it has some conductivity, or the reciprocal of that has some resistivity. And we can actually measure that. We can measure the resistivity of dough, or we can calculate it based on measurements. So by the end of today, after you guys figure out how multimeters work, but we'll put everything together and we'll figure out that. Okay. All right, you guys ready to go? So, see, lots of fun. It's Paul Hewitt time. I switch my screen over, present screen 2, share. And let's find, where is Paul Hewitt?
The source of that magnetism was betrayed years ago, more than 150 years ago, by a fellow
by the name of Hans Christian Ørsted, who was a professor type teaching, I believe he was in a high school classroom. And he was showing the students that there's no relationship between magnetism and electricity. The physics books at that time had electricity as one subject and magnetism as another. And Ørsted was showing there's no relationship between the two. And one of the things he would do is he would line up the piece of wire like this and put it over a magnet, pass a current through it, and you really don't see anything happening. There's no interaction. But after class, a student came up and held the wire in this direction, and when a current passed through it, okay, watch this, when a current is passed over the wire like this, boom, you see that interaction? It turns out there is an interaction between a current carrying wire and a magnet. And it turns out, to make a long story short, the source of all magnetism is moving electric charges. And when the charges move through the wire, they set up about the wire a magnetic field. And that magnetic field is in concentric loops around the wire. If I pass this wire through a hole in a piece of paper, and I put a whole lot of little compasses around the wire, and no current goes through, all those compasses would point north. But you know what happened if I put a current through that wire? All the compasses will line up with a field. And it turns out that field, it takes the shape of concentric circles about the wire. The further away you get, the weaker they get, but the direction is all that way. So surrounding every current carrying wire is a magnetic field that takes the direction of the concentric circles. I want to show you something that's even more interesting than what we're seeing. Let's take this magnet. I'm going to put the wire in the magnetic field of this magnet, and I'm going to touch this momentarily so I get a pulse of current. And when I do that, when a current goes through this, would this wire, in a sense, be a magnet? How about when no current goes through it? It's copper wire. Copper is not ferromagnetic. Copper, you've all tried when you were a kid to pick up a penny with a magnet. It doesn't work, does it? Because the penny's copper, okay? So the only way you're going to get magnetism with copper is to have electrons flowing through it. Electrons flowing through anything would set up a magnetic field around it, anything, yeah?
He's telling you guys one point of view, how this works for his dot show. I want to remind you guys of something. You guys remember right-hand rule? Right? No, a few weeks ago I told you a completely different right-hand rule that had to do with torque. But right-hand rule is also a term used for to tell you the relationship between I, electric current, B, magnetic field, and F, a physical force. Remember, if you have any two of those lying around with some perpendicular component to each other, the third one will pop up. Now, he's got let's think ahead, see if you guys can figure out what's about to happen. He's got a permanent magnet, so that's one of these guys, B, magnetic field, got one of those lying around. Right? He's got a wire that he's about to hook to a battery. Isn't that going to create an electric current? Right? So what do you think is going to come out of this? Maybe like a mechanical force, a physical force. Right? There's a name for that device. It starts with an M. That's called a motor. Yeah, a motor. You have an input of electric current. You run that past a magnetic field, and yeah, let's see where this is going. Create a force, right?
Let's see what happens with the magnetic field of the wire and the magnetic field of the magnet. Let's see if there's any interaction. What do you suppose? Watch this game. You see that jump down? See that jump down? Let me turn the magnet around. Jumps up. Did you see that? I'm going to do it one more time. Watch. Wow, jumped up. So one way it jumps up, and the other way, or this way, it jumps down. I wonder if that jumping motion could be harnessed. How many people say, well, no, there's probably no practical application of that. Wires will move in magnets, big deal, right? Is it a big deal? It's a very, very big deal. Because guess what this underlies, gang? Electric what? Begin with M, end with odors. Try it. Motors. Any electric motors be working on such principle, okay? And dig this. Whenever you see any electric motor, realize, you know, sometimes we see things and we're so overwhelmed with the complexities, we don't know what the nitty-gritty is. Realize the nitty-gritty of an electric motor is simply a current-carrying wire, boom, being deflected in a magnetic field. Period. That's it. This was done by a couple of physicists about the same time in history. One was Michael Faraday, a Scottish guy in England, and the other was Joseph Henry, an American type in Vermont in the 13 colonies. And they both at the same time found the same effect. And here's what they discovered. They had meters similar to this at that time, but they didn't know how to get electricity. Well, they got electricity from batteries. A fellow by the name of Volta, Alexander Volta, Italian type, made batteries, and that was kind of nice. Everyone was excited about electricity. And then Michael Faraday and Joseph Henry discovered the following. No batteries over there again. No batteries, no tricks. Magnet, wire, meter. Watch this. You see anything? No. Faraday didn't see anything either. And but watch this. Henry didn't see anything either, but watch this. Did you see something? again. My goodness, my goodness. There's no battery nearby, and guess what we are generating? Begin with EC.
Yeah. So let's think about like a right-hand rule checklist. Well, what he's got lying around. So he's got a permanent magnet again. He also has a physical force, like a mechanical force applied by his hands, doesn't he? Right. And so from that, you're able to get an electric current. Ooh. Right. Well, he has it hooked to a voltmeter, so really it's measuring the voltage, right? But that's because there is a electric. Hey, where's Pop? Hey, Pop here. Hey. I want to give you guys some notes, fill in some. Give you guys a different perspective here before I go back and fill in the rest of this. Okay. So let's you guys see 3D magnetic field. Where's so I do have some bar magnets lying around. I'll make use of these later. Okay. I do want you guys to see this field because I have this like sand timer, except instead of regular sand, it has iron filings in here, and this base has a magnet in it, so you can see like a fuzzy looking 3D magnetic field. See if I pull this off, right? The sand collapses. It just looks like blah, right? But here's my magnet right here, right? So put this on, tip it over, right? And start, ooh, hey, look at that. It's like creating a like 3D field. You can sort of see that, right? Okay. So just put that to the side. Okay. And say you have a like a bar magnet, right? Or maybe a horseshoe magnet for that matter. I don't know, so some kind of magnetic field. Okay. So draw one of my bar magnets over here. Okay. And on these magnets, maybe I should tell you just for context of my picture, since I'm using this as an example. Okay, is that the poles are actually on the faces. So this face right here is either north or south. If I flip it over, it's either south or north. Okay, we'll actually find out here in a few minutes because I'm about to. In a few minutes, I'll make a compass out of this. So we'll figure out which. Right? But the field lines go from north to south. So if this is like the north side of the magnet, then there's drawn like north to south for the field lines. So it'd be something like this. Okay, so got all these magnetic field lines. Okay, then let's say you put a coil of wires nearby this. Okay? That could be like this. There's a specific reason I have this too. Right, this coil of wires. I'll show you guys in a few minutes. Okay, looks like this, doesn't it? Okay, and there's a certain area that's roped off by this. So we got here. Should label these things. We got a permanent magnet right here. I got some wires right here, like a coil of wires. Right. This coil of wires has some area A. So A stands for area in this context. And there's some magnetic field that's running through it. So I'll multiply that area by B, magnetic field. So magnetic field. Does anybody know what the unit for magnetic field strength is? It's Tesla. You can measure how strong magnetic field is in some number of Tesla is the unit for it. Okay? And when I multiply this together, I get a quantity called flux. Flux. Right? Yeah, right? Back to the future. It's the beginning of a time machine. So multiply this together. And you know what? If this thing is rotating in magnetic field, do you think the area exposed to that magnetic field is going to also turn on and off? Right? Maybe the magnetic field won't so much, but the area would. So if I have a certain rate change of that flux, change in flux per change in time, maybe as this coil of wires is rotating, okay, call this rate change of flux, okay, then that will induce a voltage. This is generation, isn't it? Like a generator. Okay? And you know what? A generator and a motor could actually be made of the exact same components. Right? Just a generator would be taking mechanical energy, maybe like a turbine, right? Which how we create most electricity this way, right? How do you extract energy from coal or from nuclear, right? Well, what you use, you boil water, turn that into steam that turns a turbine, you extract energy that way, okay? And run that past a magnet, and that will create electric energy. Versus a motor does the opposite. It takes electric energy, electricity, run that past a magnet, and that will create the physical force, right? One last thing, this is what you guys are about to see, is that the number of coils, every time you add on another coil, and well, I'm spoiling the next part of the video, that increases the voltage proportionally. So I'm going to add something to this equation. This is called Faraday's law. So N represents the number of coils. This is called Faraday's law. There you go. So the voltage induced, right? Number of coils times the rate change of flux. Right? Flux is the area exposed to the magnetic field. You just multiply those together. Okay? Yeah. So if you're turning that on off, and how would you turn that off? By rotating the wires. That like if you have it hooked up to a turbine. Okay. I'll show you guys that in a minute too, but watch the rest of this. So switch back over to Paul Hewitt.
Electric current. I am generating electric current. And Faraday and Henry found out that. No batteries, no cells, none of lightning, none of that. Just the motion of a wire in a magnetic field. So Faraday goes to bed and he's really excited about that. And while he's in bed that night, I'm making this up now. While he's in bed that night, he's kind of thinking, gee, I wonder what would happen if I did it with 2 wires. So he gets up in the middle of the night, takes his candle, goes downstairs, had to do a candle. Little did he know that he was going to get rid of candles. I mean, the candle industry was furious later on, okay? But what he did is he went down and he took 2 wires, and guess what happens with 2 wires, Ken? Boom! Twice as much current. Goes back to bed. Then he thinks, I wonder, 3 wires. Shall we try it? Didn't sleep the rest of the night, gang. I wonder 1,000,000 wires. What do you think? 1,000,000 times as much.
Now, caveat there, if you had like 1,000,000 wires, do you guys remember something else called, oh man, it just slipped my mind as the same sentence. Hold on.
1,000,000 wires.
Digging up. All right, come back to that.
Okay? This is a remarkable discovery that one can, it turns out, induce voltage by simply moving a wire in and out of a magnetic field. And so Faraday's discovery is couched a little differently. Today it's called Faraday's law. And what it says is this, a little more complex. Change the magnetic field in a closed conducting loop of wire, and then you'll be conducting. Just change the magnetic field intensity in a closed loop, and you will induce a voltage in that loop. Now, this loop happens to be a copper wire, so the voltage in that produces a current. So look at this. You get a current. Change the magnetic field in 2 loops of that closed copper wire, 2 loops of that circuit, and guess what you get then? Twice as much voltage. 3 loops, Well, that's the rule. All you got to do is change the magnetic field.
Right, and that helped spark the Industrial Revolution, right? Okay, what I was trying to think of, what my mind was called Lenz's law. So you guys remember I showed you this before, right? So that's not magnetic, but if you drop a magnet through it, there's some resistance. Right? See, if you have 1,000,000 wires, that's kind of analogous to having 1,000,000 wires, right? Just like loop around. Right? So resistance would build up. Let's say that, yeah, you can pump up the voltage, but you don't get something for nothing, right? So energy still conserved. Right, so one more, Paul Hewitt.
Hey, you know what? You know what is a neat application of electromagnetic induction? It's just been the last few years, and that's the smart lights. When you're traveling down the road, you're coming to the traffic light, and the lights change for you. You drive over something, and that something changes the lights. They used to put like a piece of rubber tubing out there with compressed air, and it would boom, make a little pulse of air, and that changed the lights, and the rubber would wear out. What they do now is they bury in the road a coil of wire. Okay? Coil of wire buried in the road. Now, through that coil of wire is a magnetic field of the Earth. And part of that field is in that Earth, all right? Now, if you could change the magnetic field intensity of the Earth through that big coil of wire, what would you induce in that coil? Begin with a V. A voltage, isn't that right? So when your metal car drives, when your iron car, a wooden car won't work. When your iron car goes over that coil of wire, does it not alter a little bit the magnetic field intensity in that loop? Answer begin with a Y. And when it does that, it makes a little tiny electric current which activates the switch of changes the lights. Isn't that neat?
All right, so say a draw for you guys what he was talking about there. Talking about the piton, the next time you guys are driving around Vieira, look really close in the road. And when you guys come up, let me see what you guys are seeing online. I'm sure this is working. Okay, so I think we're good here. Okay. Next time you guys come up to an intersection, sketch this out real fast. Be like a dash line down the center of the road. Maybe like you're supposed to stop your car at this painted line. Something. Okay, so look really close on the road. There should be like a pattern etched in the road. A lot of these intersections come to. It might look something like that, or sometimes there's a pattern like leading up to it. Now it's basically like black, the same color as the road, so it's not supposed to be obvious. Okay. It's not official marking, but it's where they bury a wire so they can signal to the intersection that spark coming. Okay. That. What's next here? Okay, so a bunch of demos how to some cool stuff you can do with magnets and wires and stuff we can do. How can you create a compass? Well, these bar magnets, remember I was telling you guys the poles are on the faces, so I put a few of these bar magnets together. So this pole right here is either a north or a south, and this one here is either a south or north. Right? One very simple way you can create a compass is just to hang the bar magnets from a string. And the poles naturally want to align with Earth's magnetic field. Right? See, there's a certain way it's going to settle eventually. Let's try to pause it where it wants to. Right? Got a little bit of oscillation to it. So I know that this face right here is the north face of the magnet because the north face of the magnet points to the geographic north pole of Earth. Now, here's one of the things that one of those conventions that people got backwards and just kind of became standardized. You guys know that north and south attract, right? Well, people didn't know that back in the day. So they defined the north pole of the magnet as the side that pointed north. So oops, got that backwards, but just kind of stick around. So technically the south magnetic pole is up in Canada and the north magnetic pole is down in Antarctica, but oops about that. But I know that this direction is basically geographic north. Or if you guys want to make a little fancier compass, more like one you might buy in a store, just take a couple of cups, put some water in one, and then you can float your bar magnets. Now make sure that your poles are aimed horizontal. Right now it's already aligned to Earth's magnetic field, but it gives this little twist. Okay. Does this need a little more water? I think it needs a little more water. Yeah. Let's try this. There we go. All right, so now it's free to rotate. Right, so there's north, it gives a little spin. Then it always wants to rotate back and point north again. Something like that. So I get this thing to really go. Yeah, there you go. Great. So basic compass right there. And so that's pretty cool. Okay. How about what's next on this list? Electromagnetic construction. Okay, so that's why I have this bolt and this wire here. Okay. See, no, this is not magnetic by itself. See, like this paper clip. This paper clip, I should be able to pick up. Let me prove that to you guys that it can. Okay, so great. This paper clip is ferromagnetic, probably has some iron in it. Okay, probably makes sense. Okay. But this doesn't pick it up, so whatever. Okay. Until I hook some hook a voltage source to these leads. Okay. Now remember I told you guys about inductors. This is basically an inductor here, isn't it? It's just wire coiled around. So now I have to do this real fast because there's basically not a lot of resistance. This will get hot really fast, but this will temporarily create a magnet. Where I can, there you go. See, I'm picking up this paper clip. Now, as soon as I disconnect the battery, then it's going to fall apart because there's no current flowing through, so it lost all its magnetism. Okay? So that's how you can construct an electromagnet. Ooh, this battery is a little bit warm. I can feel it a little bit warm. Okay? Another thing you do, motor construction. Right, so this one, right, well, that's what this is for right here. Right? So I can take this, hook it to a couple leads on this battery. Okay? This is one of these hit or miss type demos. Actually, this one I can usually get to work pretty good, but it wasn't really working that great this morning, but it's okay, got some backups. This is actually pretty good activity if you guys are ever physics teachers one day, is to put students in groups and give them a bunch of wire and some batteries and some paper clips and also a stack of magnets. Get a stack of magnets out. I grab my compass magnets. Right. And so what have we got here? We've got a magnetic field, right? And then have students cut the wire and try to construct this. Okay, so you get this to work, but it takes a little bit of patience. Okay, so I'm going to take this coil of wires. Remember, I was just showing you guys Faraday's law. Okay, so this is kind of that backwards. Create a basic motor. Hook these stripped leads of the wire to these leads, these paper clips that are connected, of course, to the battery. Oops. Right now, right. I should show you guys that the copper wire itself is not magnetic. Right, the magnets don't pick up the copper wire. So whoops, they'll pick up the paper clip, but not the wire. Right? Wire's not magnetic itself. Right? But when you get a current flowing through it, then you can actually feel a tug from the magnet. So you kind of see it. Is this terrible? And try this with a different battery. I try this battery. Okay. Fix all it by hand. Okay, so paper clips for leads. Okay. Over the years, I found one of the kind of tenuous connections is the positive lead here. It's like if you don't get it like right on that knob, it doesn't actually connect. Oh, good. You guys saw it spinning, right? Under its own free will, right? Ooh, for the class I'm recording too. Because, right, well, okay. Okay, well, now it just spun until it spun itself off the leads. But, okay, so great, that worked, that actually worked. If I got it going, it could probably spin for a long time, right? It could spin until what? Until the battery drained, exactly, because that's the supply of energy, right? That's where the energy is coming from. When the battery drains, there's a bunch of chemical energy in this battery, right? Just ready to go. Pump it up to 5 volts, or sorry, 1.5 volts. Okay. Here's a 9 volt, by the way. This is a 9 volt battery. It's got 6 times the voltage of either one of these guys. Ooh. Okay. What's next?
Did you set it up to charge the battery?
To charge battery? No, I haven't. I used to have a battery charger. I don't think I have one still. I forget what I did with that. Yeah, years ago.
You technically could, but also the AA's don't really recharge.
Huh. Yeah, there are rechargeable. Actually, I don't know if these are rechargeable or not. It says alkaline on it. Yeah, you know what? I don't know a lot about batteries, like which ones are.
They usually make a big fuss about which ones are rechargeable.
Yeah, you're right. It probably would say rechargeable if it was. So, next thing, multimeters. Okay, so got a whole box of these. Now these, you guys, housework. What are different knobs on this? Now, multimeter, multi meaning like multiple. There are different things you can read on this. Anywhere on the top left, see where it says some number of volts, and above it, there's like a straight line and a dash line. The straight line dash line means direct current, so I can read number of volts direct current. Okay. Switch over to the right. I got volts, but it's got like that wave looking shape over it. That means alternating current. Now, what I would like to do is take these 2 leads, plug them into a wall socket, show you guys that it is 120 volts. I did that recently, and that was a bad idea. I got a scary spark out of that, so we're gonna skip that one. What else I got on here? Down at the bottom left, it says kiloohms or ohms. So, ooh, that can measure resistance, maybe resistance, something like that. That one I can't always get to work. Actually, just in general, these multimeters usually have a box of these, and then the labs I assigned, it's kind of hit or miss. Sometimes you have to go through a few of these before you go to work. Okay. There's also, there's some special knobs over here for 1.5 volt battery and 9 volt battery. Show you guys these work. So if I take these 2 leads, put them on this battery, okay, so, hey, there we go, 1.43 volts. Remember, this should have been 1.5 volts, and it's reading, where'd it go? 1.43. That's pretty close to 1.5, isn't it? Okay. It's what if I reverse the leads? What if I put the black on the positive lead and the red one on the negative lead? Hey, it's a negative number, right? Negative 1.3. Ooh, interesting. Okay. Now, why is there a special knob for batteries? Not quite sure, but what if I switch over to direct current? Ideally, it should tell me the same thing. 1.4, or what if I switch the leads here? Go back to the red on the positive, black on the negative. 1.1. Okay, then I can switch this knob to get a different decimal spot. 1.14. It's actually different from, remember before I was saying like 1.4 something, now it's saying like 1.1. I don't know why the readings are different. Maybe that's why they have a special knob for batteries. Maybe there's some special way. Right? Let me try this 9-volt. Right? So 9-volt, I hook this guy up. It's reading 7.85 volts. Okay, so this guy's clearly missing a volt. Right? Or let me switch over to 9-volt battery, see if it's still confirmed. Okay. Yeah, this is about the same thing. Or whoops, get negative number, switch the leads. Okay. So about almost 7.8 volts. Okay, so that's almost 9 volts. Right? Like as advertised. That's pretty good. Okay. Now, I do want to bring up a basic circuit for you guys so you guys can see this. Right? Now, if you play around a little with electronics a lot, you probably know that it'd be nice if I had a breadboard at this point, but I've got a video for that so you guys will see how this works. Okay. You guys remember this circuit from yesterday? These 4 Christmas lights and like this, where I'm about to hook the leads right here, where these 3 guys on the right are in series with each other, but then they would be in parallel with this guy on the left if I hook the leads like right here where these binder clips are. Okay. Remind you guys what that looks like as a waterfall model. And also as a circuit diagram. That's this guy right here, basically, right? Well, except they're all the same resistance, but basically this one, right? Okay, so I'm about to make that. Okay? So here's my 120 volts alternating current, but plug in this phone charger that jumps it down to 5 volts direct current. Okay, so now I got this leads, 5 volts DC, that's safe to touch, so it's not gonna shock me, so that's good. Okay. Then I'm going to clip these leads right where those binder clips were. Show you guys.
Might want to watch out for that puddle of water.
Oh, yeah, it is wet. Yeah. All right. Thanks for that warning. Okay, got a connection right there. Right. Then this side. Connection right there. Right. And just like you guys saw yesterday, see how there's 3 that are kind of dim, and then the bright one that's in parallel with those other 3. Okay. I wonder what the voltage drop would be across, let's say from lead to lead. What's the voltage drop? So I'm going to take this multimeter, turn it to direct current voltage. Let's try something like this. Right. Touch my leads there. Yeah. See if I get a. Oh, hey, look at that. See what it says negative 4.75? Right. Now, what if I switch the red and the black leads? Okay. Hopefully, it'll just be the same number of positive. Yeah. it's going to about 4.70. There you go, 4.77. Okay. Okay. There you go. So that's the voltage. Now, the voltage, really I'm measuring a voltage change, kind of like measuring the height of a waterfall. And so the way I was connecting that voltmeter was in parallel with the circuit. One of the lab papers we're going to get to near the end of class today looks like this. Right? It tells you how to wire up your ammeter depending on whether you look using the voltmeter function, which we just did, versus the ammeter function to measure the current. Right? Because you actually hook up the multimeter different ways. Right? It makes sense if you think about it. Remember, voltage, you're actually measuring a voltage drop, like a voltage change. So you have to go from one voltage plane to another voltage plane. That's like going from, really I measured from this green part to this blue part. That's really where the 2 leads were hooked up. So from the green to the blue, that was the difference of, oh, hey, of course it should have been about 5 volts because this is a 5 volt phone charger. So we're getting about 4.7 something. So that makes sense. That would be that, right? Versus, oh, hold on. I just moved some papers I wasn't supposed to. Here we go. Right. To measure the current, I actually have to break open the circuit. Now, I haven't done this yet, but I'll show you guys what that's. Right. I have to break open the circuit and have the electricity flow through the ammeter, right, through the multimeter. Right. A stands for ammeter because I would be measuring some number of amps. Right. Remember that current is kind of analogous to traffic flow. So it's kind of like a traffic checkpoint, right? It has to physically flow through it. And so these are wired differently. So parallel for voltage, series for current. Okay? So let me do that. And one more difference for current. So not only do I have to switch this knob over to the one that says milliamps for direct current, okay? But also, I'm not entirely sure what this is. You guys see that there are, 2 leads, the red and the black lead, but there are actually 3 places to plug them in. I have to take this red one and pop it into the, that other place to plug it in. Okay. Sure, there's a more technical term for that. Okay. But oh, and I have to break open the circuit. Right, so let me go ahead and break this open right here. Okay, then connect my leads, and hey, I'm getting a number. Okay, well, it's negative, so let me switch this around backwards. Okay. Now it says milliamps. I think that makes sense that it would be like a, yeah, it looks like about 4 milliamps, 4.4 milliamps. Okay, you guys see that? Okay. Okay, so I know the current through that part of the circuit, if I break it open and let it run through, it's like about 4 milliamps. Okay. Now this looks kind of a mess of like Christmas lights and binder clips and wires. It's kind of hard to tell exactly what's going on. So that's why for a lot of the rest of the class, we're actually going to go through videos, right, because these videos are quite pristine, won't lead us wrong. Let's see where we are in our checklist. Okay, yeah. I want you guys to learn about breadboards. So we switch over, see present, screen 2. Some of you guys might play around with breadboards if you're into electronics or robotics, which I never quite got it into a whole lot myself. So some of you guys might know this stuff better than I do. Let me find my.
Mr. Dillman has a whole set of them for his Python class.
Wait, who does?
Mr.
Oh,
Dillman.
Mr. Doman? Oh, all right. Yeah, so if you guys are taking Mr. Doman's class, then you guys will probably play around with these, right? Right? How many guys ever used a breadboard? Breadboard? Bunch of you guys have. All right, pretty cool.
Easily and quickly build electronic circuits by pushing electronic components into the holes. For example, simple circuits like this one with a battery and an on-off switch to control a light. You can also build more complicated circuits, for example, lights that flash automatically or robots of all different shapes.
Hey, look at that. You could like create a whole robot with a little breadboard and a bunch of little parts. Pretty cool.
Sizes. There are far more examples than we can list in the beginning of this short video. At this point, you might be thinking that this doesn't really look like it has anything to do with bread. The name breadboard comes from the early days of electronic circuits when people would literally use wooden boards with screws or nails driven into them to make electronic connections. Modern breadboards are made from plastic and come in all shapes, sizes, and even different. With an adhesive backing that allows you to permanently stick them onto a project. For example, the breadboard stuck to this robot. If you remove that backing completely, like I've done with this breadboard here, you expose a series of metal strips that are inside the breadboard.
All right, here's a really important pause point. So you can see it, because one side of the breadboard just looks like a bunch of holes, a bunch of dots, right? But behind the scenes, what's going on? Well, you got 5 holes in a row that are connected together, right? Now you'd want to know those are connected because say you put 2 leads of some device on the same row, set of 5 holes there. Well, that would just like short out that device. It'd be completely pointless, right? But say if you like bridge the gap between, there's like a gap between the two. So if you bridge it, then you can start to like piece together a circuit, right? You can see from the top point of view how the circuit's going together, right? Right, then you got these 2 on side. These called what, rails or buses, I think. Is that right? Right, rails, right? Yeah.
These metal strips are what make mechanical and electrical connections to the components you insert into the breadboard. We can remove one of these metal strips by pushing it out from the front to see what it looks like up close. Each strip is a series of 5 clips that line up with the holes on the breadboard. When you push a component into the breadboard, these clips are what's actually grabbing onto the leads, like you can see here with this LED. This breadboard is actually made from transparent plastic. Circuit. For example, all of these holes are in column C, and all of these holes are in row 12. Hole C12 is where column C intersects row 12. Blue marked and are used to deliver power to your entire circuit. Typically, the red one marked with a plus sign will connect to the positive battery terminal, and the black or blue one marked with a minus sign will connect to a negative battery terminal. Some breadboards, like this mini one, do not have power buses at all. F1, G1, H1, I1, and J1. We'll explain more about what this gap means in a little bit. This diagram shows all of the connections on the breadboard highlighted with yellow lines.
So that's like what you guys saw before with the metal, right? So you guys know what holes are connected to which one. Let's see. Here we go. One of these actually wired up, right? look what he's got going on. It's got a voltage source, it's got an LED, he's got some wires connecting, right?
Pretty simple.
Jump wires,
Now let's zoom in and see how I actually have everything connected on the breadboard.
got a resistor over
The
here.
battery pack's red lead is connected to the power bus on the right side of the breadboard. This is connected to a jumper wire that goes to row 5, which then goes to the LED, over to row 5 on the other side, to a resistor, to the ground bus.
You guys see these colored bands on this resistor? You can read those colored bands and figure out how many ohms it is, or kilo ohms or kilo ohms. I don't know off the top of my head how to memorize these, but I guess you could Google that if you're interested. Some of you guys might go. Does anybody know, be able to look at that and tell me how many ohms that is? Okay, well, you could though.
And then to the battery pack's black lead. This diagram shows how electricity flows through the circuit using yellow arrows. This is called a closed circuit, or a complete path for electricity to flow. Remember that on each separate half of the breadboard, the holes in row 5 are electrically connected to each other. This means, for example, that I can take the leads of the LED and move them to different holes in row 5 and it will still light up. However, if I take the LED and move it to a different row entirely, like row 4 or row 6, it does not light up because
So that would be an open circuit, right? So the electricity does not have a closed path to flow.
there is no path for the electricity to flow. It has to be in row 5 to have that path. You can also reconfigure the entire circuit. For example, here I'm going to move the LED and the resistor over to the right side of the breadboard and then connect the battery pack's negative lead to the ground bus on this side. While this looks different, electrically it is the same circuit, so the LED still lights up.
Yeah, it's talking about polarity. So I'll show you guys this later too, but LEDs, you can only put them one way. Like if you reverses it, it doesn't actually turn on. You guys see that later. Okay. Okay, then last few minutes here, he talks about what you can use for jump wires. So you can either use these like loopy wires like that, but then those can get kind of complicated. Oh, like if you have a real complex one, right? Or you can buy these standardized jump wires, right? Or you can just buy a spool wire and just cut your own, right? So you can get them like exactly what you want. All right, so there you go. There's an intro to breadboards. Okay. Now let's switch over and look at which guys
Just like you would with any other component.
see it's all put together. A guy using a breadboard and a multimeter. Okay. Oh, actually, I want to skip a bunch of this specifically. Right, so you guys see a breadboard. You guys see he's starting to hook up some stuff, right?
This line here is not, or it's a break in between both of these.
Okay. So now this is not a complete circuit yet. He's still building it, but see if you can kind of figure out what's going on. Now he has each of the leads of each of these resistors. You guys do see 3 resistors, right? Resistor, resistor, resistor. See those colored bands, right? You could read those and figure out how many ohms they are, but we'll know by the end of this what they are. Okay. Now there is a break in the middle. So these two guys on the right here could be connected in parallel with each other, but just kind of like an isolated island. Right. Now this could be a voltage source on the left. Well, a place for a voltage source, but doesn't have that quite built. Right. Now he's going to put it. There's his jumper wire. Right. Put in a couple of jumper wires. Now he's connected. From one side, think of it like a bridge, right? So now, actually I'm giving away more than I need to give away. We're going to use this video for part of a lab. So you guys got that lab page out? Look for the one that, where did I put it? Oh, here it is. Okay. Look at the one that says Kirchhoff Table Circuits Lab. Okay. So that's this page right here. All right, now in this space here, and it actually did refer that here. I said draw each circuit on the left, use the multimeter table on the right. We're just going to do one circuit. We're going to do the one that he's in the middle of constructing right now. Right. So I'm going to flip back, and I want you guys to draw a circuit diagram for what you guys are seeing. See if you can look at his breadboard and draw the equivalent circuit diagram. Actually, you can use like all the space if you want, because we're just doing one of them. So use this blank space to draw the circuit diagram for what you guys see. Of course, I'll show you the answer in a minute, but I want to see if you guys can use your own brain power to figure this out first. Okay. Let me go ahead a little bit, because he has to add a little bit to it. remember there's also a break right here, so he has to connect these resistors to the rails, right? You guys are calling the rails, or you're calling the buses, right? Remember there's a wire that runs all along here. So he's got that connected, and finally he plugged in a voltage source. All right, so there you go. There's the complete circuit. See if you can take that breadboard scenario and draw the circuit diagram for that. Draw the circuit diagram. Okay, so if you know what you're doing, go ahead. If you need some hints, then remember that, okay, so I see 3 resistors, right? Resistor. I see imagine this is the voltage source on the left with the red and the black leads. Okay. Looks like he's got some jumper wire connecting the leads basically to, well, the area that has the resistors in it. Okay. And then remember, each of these rows of like 5 holes, so got five, they're all connected to each other. So I know for sure that these 2 resistors on the right are connected in parallel, at least, right? Because he's got, they've got the leads each in the same row. Okay? But also, you know what else? There's also some jumper wire that connects it to these like 5 rows on the left side, right? So like 5 and 5. Hey, that's going to bring in this third resistor also, right? And then those are furthermore connected to the leads of the voltage source. Huh. Right. You guys figure out what that circuit diagram looks like? Right? Yeah. See some of you guys on. Who thinks they know for sure? Wants to share? What they got? What'd you get, Eric? Good. You're saying 3 in parallel? Is that what you're saying too, Kevin? Right? Yeah, Morgan got that. Okay, you guys got 3 in parallel? That is 3 in parallel. Yeah, that's 3 resistors in parallel. So we switch over to projection. Draw this with you guys. I'll just do sideways just to make use of the space. Okay. So we got a voltage source on the left side. Then there's 3 resistors in parallel. Resistor. Now, they might be different resistances. Actually, they are, but let's okay, we'll call them to that idea. Right? So you guys see this little tiny Kirchhoff table? This has 3 possible resistors on it. We can just use this table for the rest of this this lab. Right? Maybe I'll call this resistor A, B, C. Right? Or if you wanted to label them the other way, there actually could be a good reason to do like A, B, and C opposite of what he did. Right? Which is that to find equivalent resistance, you start from the outside and work back towards the voltage source. So using that method, you'd actually do CDA, the way I drew it. Okay, so that's what we got. Now, he's going to take a multimeter. Remember, one of these guys, right? He's going to hook it up in parallel with each one of the resistors individually to get the voltage drop across each one. And then later on, he's going to break open the circuit and switch this over to like the ammeter function to get the current going through. Okay, right. And then we're going to fill out these 2 middle rows and then figure out everything else based on that. Okay, and so switch back over to computer, okay. And we'll just go on with the spectrums here.
Go ahead and turn on my voltage supply.
All right, let's go ahead a little bit. So there's this voltmeter. Here we go.
It's a little bit tough. You'll notice that I have 4.95 volts. 4.95 volts. Good. In fact, let me just
Yeah, there's some glare there, so it's going to prop it up, so it makes it. But for the first one, he keeps getting the same number. It's like 4.95 volts. So
cross resistor number 2.
Okay, pause right there. All right, so for the first voltage drop across resistor, well, the resistor closest to the voltage source, which I've got listed as resistor A, I'm going to call it 4.95 volts. Okay. Now, hopefully you guys know enough about these circuits at this point that you can figure out, like, even if these resistors are different resistances, do you think that the voltage drop across each of the other ones should be much less than, much greater than, or about the same number as that? Should be the same because they're all in parallel, right? It's like, yeah, same height waterfalls. This could be side-by-side waterfalls, couldn't they? Right? They might have different currents going through them, but they'll have. But let's verify that experimentally here. Or have this guy see what he gets.
Make sure everything is in.
What? 4.95.
Resistor number 3. .95 also. So those are the 3 voltages across the resistors. All right. Now, in order to check for the current, what I'm going to need to do is to break the circuit in order to check for the current. Since the bottom here is a little bit more accessible, I'm going to actually break the circuit at those points at the bottom. So in order to find the current for resistor number 1, what I'm going to do is I'm going to remove that resistor from the line there. Okay, remove that resistor from the line. And then what I'm going to do also is I'm going to put a wire into the circuit where that resistor came from. So that's in the same line there. And to check the current, I'm going to need to turn this over to I'm going to use 2 milliamps. And I'm going to
make some adjustments here, so skip ahead a little bit.
And I'm going to get a current. Let's go with 200 milliamps instead. 200 milliamps. There we go. All right. And so what it says now is I have 3.3 milliamps.
3.3 milliamps, right? 3.3 milliamps. Guys, milli, that's a factor of what? 1 over 1,000, right? Right. So for current in amps, I'm going to put 3.3 over 1,000, right? Because that could be the number of amps, right? 3.3 over 1,000. Right. All right. So we got our first current. Now that's the current through resistor A, right? That's not necessarily current through the other ones, though. So let's see what he gets through the other ones too. And so back to computer.
So current going through resistor number 1.
Right. So then he puts that back together. Then he breaks it near resistor B, and then connects the leads here.
The wires here on each of the, let me see if I can get around here, on each of the wires. So I'm touching the wire that I inserted, and then the resistor I pulled out of the circuit here, and I end up with what?
Basically 1.0, right? No, negative. Why is it negative? He's got his leads backwards, right? Yeah, so black and red. Okay. But the magnitudes, right? So we're going to go with 1 milliamp. So on the table, I'm going to put 1.0 divided by 1,000 because that could be the number of amps, right? Milli is 1 over 1,000. Okay. Okay. Then finally, let's see what it is for the last resistor.
1 milliamp, and it says.
So he has to put that together. Remember, he had to break it apart to measure in the first place because that's how you measure current. So he puts that back together. Then he breaks the circuit here, resistor C.
Let's make sure that resistor is in there. All right, and it's saying that the current going through there is 5.0 milliamps.
5.0 milliamps. All right, that's all we need. So switch over to projection. Stop sharing my screen. Okay, so that was 5.0 out of 1,000 amps, right? 5 milliamps, 5 over 1,000, right? Let's see what you guys are seeing online real fast, because I know I made little tiny boxes. Let me hold this closer to the camera so you guys can for sure see those numbers, right? All right, so that's all the starting data we need to figure out everything else. Let's go back to resistance. I wonder what the resistance is of those resistors were. Right? Of course, they were marked with colored bands, so I guess we could have read it directly, but we can also use whose law at this point to figure that out? Starts with an O. Oh, Ohm's law. Not a very long word. So you guys remember current is voltage drop acting on resistance? Right? It's not too uncommon. You'll see it written this way, V equals IR, right? Which is one step away from figuring out resistance, is voltage acting on current. Let's use that right there. Okay? So I've got, for example, 4.95 volts divided by, see, 3.3 out of 1,000 amps, right? So 3.3 milliamps. Right. So this would be 4.95 volts acting on 3.3 over 1,000 amps. That gives me exactly 1,500 ohms. 1,500 ohms, right? That's right here. Ohm's law. So that's this box right here. It'd be 1,500 ohms. Okay. And but we could just do the same thing for the other ones, right? So we got 4.95 divided by 1 over 1,000. Before I show you guys the answer, guys, the fact that resistor B has less current flowing through it, does that mean it has more or less resistance? Less current, that means more resistance, right? Okay. So I hope resistance is more than 1,500 ohms. And yep, it came out to 4950. Okay. Maybe you guys are staying a step or two ahead of me, which would be a good idea too. Okay. So you guys were getting 4950 ohms for resistor B. Okay. Oh, couldn't you also call that 4.95 kilo ohms? And 1,500 ohms, you could also call 1.5 kilo ohms, couldn't you? It's common to use see something like that. Same thing. Idea. Do you ever see that? And then the last one, resistor C, the same voltage drop, but now we've got 5.0 milliamps going through. So that's, did you guys get 990 ohms? Right? Really close to, I wonder if that was supposed to be 1 kilo ohm. It probably was. That's probably what it was marked as. 1,000 ohm, right? So, yeah. All right, so now we know the resistances of these things. It was probably supposed to be 1.5 kilo ohms, 5 kilo ohms, and 1 kilo ohm. I'm guessing. And so power, I gave you guys a few formulas for power, but the one on AP's equation bank, which is probably most straightforward right now, is P equals IV. So we can make use of that. Power is current times voltage. Okay. Let's try that out. See if you guys can figure it out before I write down any numbers. All right. We're doing power is current times voltage. So current 3.3 over 1,000 amps times voltage 4.95 volts. I'm looking at, okay, so these are going to be really tiny numbers. 0.016 watts, 16 milliwatts. Okay. The next one, just change this number out. I'm getting 0.0050, basically, 0.005 watts. Okay. And then the last one, if I pop in a 5 right here, IV. Okay. I'm looking at 0.025 watts. Okay. So tiny numbers of watts, like milliwatt range. Okay. You guys good? Okay. Oh, and yeah, let's do it for the entire circuit. See what's the voltage source experiencing. Okay. So what's the equivalent resistance? Well, the fact that there were 3 resistors in parallel, because you guys said they were in parallel, right? Should I add up these resistors, or should I treat it like painting a fence? Painting a fence, right? Remember, 1 over the total resistance, equivalent resistance, is 1 over the first guy, plus 1 over the second guy, plus 1 over the third guy. Okay. Okay. So I'll just do that on this calculator all at once, because you guys can figure that out. We've done enough of those over the last few days. So it's 1 over 1,500 plus 1 over 4,950 plus 1 over 990. Then take the reciprocal of that. I'm getting an equivalent resistance is 531 ohms. Okay. So 531 ohms. You guys getting the same thing? Okay. You guys are doing this too, right? Okay. Okay. Then what What should I put for the voltage drop across the voltage source? Yeah, 4.95. Right. See if I color these with voltage planes, like I've been doing like yesterday. Yeah, and also on Friday I did some of these with you, right? So they're basically 2 voltage planes, right? So yeah, of course the voltage drop is going to be the same across each resistor, and also that's the voltage supplied by the voltage source. I bet that was a 5-volt voltage source, right? 5 volts, and it landed a tiny bit short because a lot of times these are not exactly accurate. Right. What's the current? Well, I could just use Ohm's law. Current is voltage drop acting on total resistance in this case. So that could be 4.95 volts on 531 ohms. That gives me 0.0093. So that's like 9.3 out of 1,000 amps. That's 9.3 milliamps. Okay, 9.3 milliamps. You know, the other way I could have gotten current is I could have added up each of the currents coming from each of the resistors, right? Kind of like adding up traffic coming from 3 different roads, all driving in the same parking garage. What is 3.3 plus 1 plus 5? Oh, it's 9.3. It's the same. So 2 different ways to get this number. Okay? Add the currents or do Ohm's law V over R for the whole circuit. Okay? Then finally, power. So we could use P equals IV is one way to do it. So let's do 9.3 over 1,000 for the current times the voltage of 4.95 volts. I'm looking at 0.046 amps, or sorry, watts, right? 0.046 watts. Right? The other way to get the power is to add up the individual powers. So what is 0.016 plus 0.005 plus 0.025? Oh, it's the same number, 0.046 watts. Okay. So either perspective leads you to the same spot. Show you guys online because I made a little tiny table there. Okay. Okay. You guys get that? All right, so that takes care of that. Next one. That's all we're doing on that side. Okay. If you flip this over, we've got resistivity of dough lab. Ooh, this should be fun. Get to play with Play-Doh. So break this out. I wonder what the resistivity of this dough material is. Okay? Because remember I told you guys that resistivity, of course, is a material property. Like a copper wire and an aluminum wire will transmit electricity differently. But how? It has to do with material property.
Do optics generally conduct more electricity when they're cold or hot? I believe it's colder is more conductive.
That's a good question. I don't know. Does anybody know the answer to that question? Are materials more conductive if they're hotter or colder? Actually, it is colder. I know that. Yeah, it is colder. I remember like very famously, drag as a side graph here, that if you look at what's the resistance of some material, either resistance or resistivity, maybe I'll just do resistance, as a function of temperature, okay? It's kind of linear. So as you make the temperature colder and colder, the resistance actually gets less and less. Less resistance means more conductive. Okay. Now there will be some place where if you reach really cold temperatures, let's say like negative hundreds of degrees Celsius, okay, where suddenly the resistance will drop to 0 all of a sudden. This is one of those like surprise findings in science. Okay. Does anybody know what the name of this phenomenon is? Superconductivity. Yeah. And there are lots of advantages to superconductivity, right? I mean, no resistance. That's like a magical situation, right? The catch is that you have to create really cold temperatures. Now it's different temperatures depending on the material. So one thing that engineers are on the hunt for is there material that could go superconductive at like a reasonable sort of room temperature? Because you could do all kinds of cool stuff with that. But it's a side note to what we're doing here. So do you guys remember? So I got my dough tube. Now this tube, this could look a lot like maybe like a wire, couldn't it? Maybe a cross section of a wire, okay? Where it has some cross sectional area. I could call that A. It has some length. I could call this length L. And it also has some resistivity, which I'm going to call rho. So rho, in different contexts, it might mean density, but in this context, it means resistivity. That's this right here, measured in ohm meters. Okay, yeah, that looks like this, doesn't it? Could also be like a copper wire or something like that. And the formula that we've been looking at is resistance from end to end, say from this end to this end, is equal to resistivity times the length divided by cross-sectional area. Okay? Should make sense too, right? The longer it is, the more resistance. The greater cross-sectional area, the less resistance. Ooh, that makes sense. Easier for electricity to flow through. Right, but what is it for this dough? Now I do want to show you guys that electricity does flow through this. So I'm gonna hook up my my phone charger go.
Is it right next to the
It probably is. Okay. You know what? Closer things are in front of my face, the less I see them. I'm sure you guys see it, but it's invisible to me right now. So I've got a backup right here. It's got this 5-volt. I'm sure it'll pop out. All right. Plug this in. Right, so I got these 2 leads. Right, so remember 5 volts direct current. So if I hook them like this, yeah, at this point, there is electricity flowing through this dough cylinder, but how would you know? Okay. Oh, that's why I brought along some LEDs. Okay. I'm gonna break this apart to show you guys for sure this is flowing through. Okay. So, well, if I had my leads here, this would be open, it'd be broken open. So I need to close the circuit. I can do that with an LED. Now remember how LEDs have polarity, so the electricity only flows one way? So I don't know which way this is gonna go. It's a 50-50 shot. Right. Actually, one of these leads should be a little bit longer than the other, so you should be able to tell, but I'm just gonna trial and error this thing. Okay. Oh, I put it in the right way. Wow, that's amazing. I thought Murphy's Law was gonna strike like it always does, but apparently not. Got it on the first go. Oh, we got a color changing LED. Look at that. Now it's kind of blue. Now it's purple. So it keeps changing colors. Oh, I think a special one. That's very nice. And so electricity must be flowing through, obviously the LED, it's turning on, but also the dough, because the dough is part of the conductive material now, isn't it? Okay. What if I take these leads and move them really far away from each other? I wonder what the brightness is gonna come to the brightness. It's only so far I can. Ooh, what if I turn these like this? Get a longer distance that the electricity has to travel. Oh, it's not, I don't even see a light at all. Okay, move this closer. Wait a minute, did I get these wires backwards? Maybe that's what happened. Yep, that's what happened. So now it's back on. Okay, but what if I give it a longer distance to go? That still turns on. Is it brighter or dimmer? What if I put it right on the leads of the LED? Whoa, now it's super bright. Okay, so there's definitely some voltage drop across the length of this dough, isn't there? It's losing some voltage. Low voltage drop across the LED itself, right? Right. So that's evidence of that, right? Okay. Right, so pull this apart. Right. This is all right. So you know what we could do is imagine I had these leads here. Okay, is if I had these 2 leads like this, I could measure. What would this be good for? Measuring a voltage drop or a current? Right. Let's say I had a lead here and a lead here. You guys see that this would measure the voltage drop across this section of the dough, right? Versus if I wanted to measure current, what I'd have to do is do something like break this open, put this lead here, and connect the other lead to, right? Do something like this. Then the current could flow through the ammeter, right, through the multimeter, right? But we'll do a similar thing for this one that we did for last lab page. Is we're gonna play off a video since the video is perfect and it's easier to see. And right, so back to here. Let's find resistivity.
Resistance depends on an object's resistivity as well as its shape, such as its thickness and length. Unfortunately, we can't just switch the multimeter to ohms and then stick the probes in to measure resistance, because there's actually a significant amount of resistance in the interface between the metal wires and the Play-Doh. Instead, we'll use a power supply to run a constant voltage and current through our Play-Doh wire. and then use a multimeter to measure the voltage drop between different points of the wire. We'll put down a ruler so we can get the location of our different voltage measurements.
All right, here's where we have to use video evidence to figure this out. I'm gonna need your guys' help on this one because I think you guys can see this a little bit better than I can, my angle. Okay, one thing we have to figure out is what is the cross-sectional area of this dough cylinder, and to do that, we can figure that out based on the diameter. I want you guys' best estimation. What do you guys think the diameter of this is? Seeing the ruler kind of side by side. You're saying
What is the diameter?
about.
And it depends on where you're measuring.
Well, let's just say in general, like from here to here. So look about 2, is that right? Or do you guys think more than 2? 1.5. Would you guys say 1.5? Okay, yeah. So I'm gonna go with your guys' word on that because I think you guys got a better angle on that. So let's go with now 1.5 centimeters. How many meters would that be?
0.01.
Yeah, to be like that, right? Okay, so yeah, if you put it in meters, now this dough cylinder is going to be the same, so this number will be the same all the way down. Right, we're not changing the cylinder. Right? Cross-sectional area. You can get cross-sectional area based on the diameter. Right? Some of you guys might know how to do this already or be able to figure it out, but so you guys do this. So you guys know circle, right? Circle, the cross-section we're looking at, right? So the electricity is like going through like into the paper, right? Has I'll call it radius r or diameter d, right? Radius r, diameter d, right? And where you guys know that diameter is equal to 2 times the radius, right? Or actually, remember the other way around. Radius is half the diameter. Okay? So that you guys know some equations about circles, right? What's the area of a circle? Yeah, pi r squared. Yeah, I always have students that mix up that one versus the circumference of a circle, which is 2 pi r. Right? Yeah, if you ever mix these up, here's a quick way to distinguish them. Circumference is a linear value, just like radius is a linear value. You can measure that in like meters or centimeters, right? Area, don't you have to measure like square meters, square feet, right? That's where you're going to square the radius, right? You get some square unit, like square meters. Okay, so we're going to play off this one, cross-sectional area. Knowing what the diameter is. Now, since radius is half the diameter, maybe I should take this and substitute it right there, right? So could that give me area is pi times half the diameter squared? And then couldn't I take that 1/2 being squared and pull that out in front and get area is, this is the one we're going to use, pi over 4 diameter squared. Okay. So if you didn't know before, so you guys know area is pi r squared, but it's also pi over 4 times diameter squared. Yeah, you guys good? All right, so go back to here. Let's do that. Let's applying this right here to this section. Cross-sectional area. Let's go pi over 4 times 0.015 squared. And I'm getting a tiny, tiny number. This is 0.30 177. Yeah, okay, it's probably too many digits, but that's okay. Right? Like that. That's the same number all the way down. So just copy paste that number. Square meters. Okay, like that. There you go. There's cross-sectional area of that dough cylinder. Okay. Now length. Now this he's going to treat as an independent variable. Okay? And he's going to get different lengths. He'll do lots of them. We'll grab 3 and then figure it out from that. So switch back over to computer. Say present screen 2, share. I think I was sharing this before. All right, so you guys see the basic setup, right? We got electricity in one end, electricity out the other end. So electricity's flowing. He's got a dough cylinder here, and he's got the lead to this multimeter. He's got the black lead connected right here, and the red lead hooked to this far end, so that the voltage drop it's measuring right now corresponds to this length of the cylinder. Let me roll this ahead a little bit. Go start at a specific place. Okay. So this is his actual first spot. Okay. So since you guys have a better view than I do, from this black lead here to the end of the cylinder, what is this length in centimeters? Looks like just over half a ruler. 18? I can believe that. Let's go with that. So let's call that 0.18 meters. Okay, 0.18 meters. Okay. And you guys see the voltage drop that corresponds to that? It's 7.83 volts. So under voltage, put 7.83 volts. So length 0.18 meters, voltage 7.83. Okay. Now we don't have the current yet, but hold on to that. We'll get that at the end. Okay. Then what he does is he moves this black lead incrementally. So let me scroll ahead a little bit. Let's say like right here. Here's probably a good spot, right? Guys, from here to here. So again, need you guys' that's call. How many centimeters is this from here to here? 10? You guys say 10? Okay, believe that. So let's go 0.10 meters, and what's that? 5.83 volts. Okay. Oh. We're doing from here to here. Okay. Yeah. Because the two leads will tell you the difference there. Okay. Scroll ahead a little bit more. So see, he's moving incrementally. He's really getting lots of data points. Okay. How about this one right here? How many centimeters about?
Like, really? I've seen one.
Yeah,
from the end of that metal thing to the
guys saying about one?
black thing.
Something like that? Okay, let's try that. Okay, now it is okay, so 0.01 centimeters, guys saying? Okay, now it's 3.61 volts. That does seem like a too large of a voltage drop, but that's all right. I mean, empirical numbers are empirical numbers. So got the readings what we got. Okay, so the next thing we need to get is the current. So if only we had the current, we can finish this off.
Once we have all our voltage measurements, we disconnect the wire from one end of the Plato, switch our multimeter to measure amps, and connect it in series with our Plato wire to measure the current passing through the entire circuit.
See how he broke the circuit open? He's going to connect the lead directly to the end of the dough, right? But the current is forced to flow through this multimeter, through the ammeter.
Now we can use the currents and voltages together with Ohm's law to determine the resistance of each length of wire.
Right. So it looks like about 14, I think it's supposed to be milliamps. Okay, 14 milliamps. You guys got that? Right? That's all we need. So I'm going to switch over to the projection. Disconnect the sound. Second. Someday I will be a full robot. That was 0.014 amps, right? Like 14 milliamps. Right? That was, let's just go ahead and apply that to all the circuits because just one basic circuit, right? So the current flowing through should have been about the same for all the scenarios. Right. All right. That's the raw data. We can use Ohm's law to figure out what is the resistance. Some paper here, right? So you guys remember Ohm's law, V equals IR is one way to write it. I want to get resistance. Resistance is, see, voltage drop acting on, or divided by the current going through it. So V over I, that would be this many volts divided by this many amps. Okay? So figure out the current. So I got, oh, actually we're doing really good on time. Ooh, yeah, we got plenty of time. Got 9 minutes here. So resistance. So V over I. So take my, oh, stop sharing my screen. This makes more sense for. All right, so we're doing 7.83 volts divided by 0.014 amps. That is 559 ohms. Okay, so that long section of dough had this many ohms. Okay. Then the shorter section, like the middle section of dough had 416 ohms. If you divide these two, 416. Okay. And then the little tiny section that was only like a centimeter long, so it's 3.61. Okay. Looking at like 258 ohms, right? Now that is those numbers I would not have expected to work out exactly like that. Now they should definitely be getting smaller if the length that the electricity is passing through is getting shorter and shorter. Yeah, the resistance should definitely be going down and down. I would have expected this to get a lot less, right? Like if you had say like a tenth of the length, it should have been about a tenth of the resistance. This number should have been a lot smaller, but that's all right. All right, now to get the resistivity, two different perspectives I want to tell you guys about. What you guys are probably thinking about is this formula right here. Right? Couldn't you just rearrange this and solve for resistivity? Because we have everything else. Resistance, check. Length, check. Cross-sectional area, check. Right? Have all that. You can just get this equation form, and we'll go ahead and do that. If this were an AP question, which I know you guys aren't going to get an electricity question on the AP, but their thought process. Remember, AP loves graphs. I'll fit in a graph before you guys walk out of the classroom today. We'll do like resistance versus the quantity of L over A, right? See R versus L over A. This would be like Y versus X, where ideally these dots should line up in a straight line where the slope represents resistivity, right? That's an AP type thought process. They've asked a question similar, extremely similar to this. Actually, they have asked this question in the past. Right, so, but let's try the equation form. So I could say resistance is resistivity, length over area, solve for rho. So the resistivity should be resistance times area divided by length. Just algebraically rearrange that. I bet you guys probably already have these three cells filled in, so I'll pop these in. So resistance 559 ohms times 0.000177 square meters for the cross-sectional area, divided by the length of 0.18 meters. That gives me, for the first one, 0.55 ohm meters. Next one, I need to change this number to 416, but everything else is the same. Cross-sectional area, or no, that's not true. Scratch that. The length also changes. Cross-sectional area is the same. Length changed to 0.10 meters, 10 centimeters. That gives me 0.74 ohm meters. And then the last one, say 258 ohms times same cross-sectional area divided by 0.01 meters long. It'd be, ooh, well, this would have to be a big resistance because if there's really that much of a voltage drop over that short distance, that would have to have been the case, right? So yeah, this number looks like a complete outlier, but that's all right. At least 2 out of 3 measurements, we got something that's pretty close to the textbook answer. We got about between half and 1 ohm meter for the resistivity. Right, you guys see that? Right. Oh, are we good? Right, so that's all we're doing on the slide page. Now, hang on to that just for a couple minutes here. Let me present my screen. Present screen 2, share. I want to show you guys 2 things on the computer. One thing I'm going to show you is what is the resistivity of clay dough. Let's see how close we were to the textbook answer. I think it says it right here. Yeah, 0.24 ohm meters. You guys see 0.24 ohm meters? So our numbers weren't that far off. At least the first two, like 0.55, 0.74. It might also depend on some other factors, maybe like, I don't know, temperature, humidity, the dye they put in the dough. Right? It could be. I think different colors are slightly different. So yeah, but yeah, so that's definitely the correct order of magnitude. And the other thing I want to show you guys is how you could construct a graph using that data that we have. So you guys remember that AP loves graphs? We've done a lot of graphs for the labs throughout the semester, but I normally have it pre-programmed where the numbers just pop in and it makes a graph for us. But I want to show you guys how to construct this from scratch. So let's go, see, put resistance in ohms. Let's go length in meters. And let's go area in square meters, like that. Okay. So the resistances were 559, 416, and 258 ohms. Okay. The length of meters, those were 0.18, 0.10, and 0.01. Okay. You also a decimal place to that. Oops, wrong way. Okay. And then the cross-sectional areas went 0.000177. Okay. Then I'm just going to copy paste that number down there. Okay. I'm going to create a special column, which is length over area, okay. Just like I showed you guys a moment ago. Okay. And I'll say equals. Once you type in equals, Excel's ready to calculate something. This length divided by this area equals that ratio. Then just take this corner, drag it down. Okay. And it will do the subsequent calculations for those other rows. Okay. Now I want to graph what is resistance in ohms, like this, on the vertical axis compared to what is this ratio L over A for my horizontal axis. Okay. So I'm going to insert, I want a scatter plot graph, this one right here. So when I use my software, right click, select data, right? Add data. Okay. Series name, don't care about that. Okay. X values. My X values are this ratio, L over A. Put those three in. The Y values is going to be these three guys right here. Put those in. Right. And actually, that's not too bad. I don't know. Ideally, this should have been a straight line that goes through the origin. That's what it should look like. So looks kind of like that. Okay. What you can do too is you can right click on one of those dots, go to add trend line, and hey, what just happened? That's my computer going all haywire. Okay. Display equation on chart. Okay. Remember, the slope should represent the resistivity. Okay. So pump up this number. Okay. So the slope of that graph should represent the resistivity of that dough. 0.31. Yeah, that's kind of in that ballpark too. It's pretty close to the textbook value and kind of close to what we got for 2 out of those 3 trials. Right? Right? You guys good? Any questions? Any questions? All right. So let me stop this recording since we got about 2 minutes left. If you're online, then upload that both sides of that lab to Focus. If you're in class, you can pop that in the grade tray. And you guys have a couple minutes to shock yourself on the band.